All right, today we're going to discuss what we actually started in the class, a couple of class periods ago, the classification tree, right? Classification tree is actually the first analytical technique, data mining technique that we're going to study, all right? And this is a supervised learning. We discussed it, right? Why is it supervised learning? Because I'm trying to predict a certain variable, which I call target variable, based on other variables in my data set. So one variable that I'm predicting is called target. What I'm using to predict the target, they're called predictors, right? Or independent variables. Now this is the example that we did in class. Remember that? We said that there are 12 people, right? That came to the bank and they took out the loan, all 12 of them, right? Some of them defaulted, and that's being denoted as a yes on the top of them, right? And some of them did not default, so they paid back loan, no problems, right? And therefore, for them I have no default, right? And you can see that people are, we're going to do that example all over again, right? What's different about my customers? Well, three things, right? They all have different head shapes. There are rectangular heads and circle heads, right? They also all have different body shapes, ovals versus rectangles, right? This is an oval, this is a rectangle. And they have different body colors, right? There are a couple of people with gray body and the rest of them are white bodies, right? And remember what we did, we said, let's see how we can create the most uniform or homogeneous groups out of that, right? Why do we need that? Right now, there are 12 figures, right? 12 customers. And out of them, how many are not default customers? 1, 2, 3, 4, 5, 5, right? Is it 5? Yeah. 5 customers did not default. And 6 customers, they say yes, right? They did default. So I have a mixture, almost 50-50, right? Not quite. 50-50 would be 6 and 6. Well, I have 5 and 7, right? Split. So it's almost 50-50. So if I'm going to, if the next customer comes into the door, they have, for example, white body, rectangular body, and circular head, right? I want to know right off the bat whether or not this customer is going to default on the loan or not default. Well, if it's 50-50 in my group, I can just, flip a coin, right? Essentially. Like, let's toss a coin, heads, they're going to default, tails, they're going to be okay, right? So right now I have no way to determine what's going to happen, okay? And what we did in class, just a reminder, right? We tried different splits. What if we take the whole group and split based on the head shape, right? Rectangular heads, squares really, right? Squares versus circles, right? So what kind of groups are we going to get as the result of that? So what I want to do is find the variable that gives me the most even split. Not even, but the resulting subgroups, they're as uniform as possible. Ideally, all people are yeses, all people are no's, right? If I have a mixture of yes and no, that's not so good for me, okay? So what did we decide? Do you remember? What was the best way to split?
If the body matched the head shape.
If the body, we were trying to do one variable at a time, right? Based on the body shape only or based on the head shape only. So there are no 2 variables simultaneously. What was the best split? You remember? What was the best variable to split on?
Was it body shape?
Body shape, right? Body shape. So let's actually take a look at something that's not part of your textbook. I just wanted to put it out there, okay? So bear with me a little bit. In 1950s, a group of scientists developed something that's called a theory of information, okay? Information essentially is a way to organize data, right? So organization, the word information is equivalent of the word organization, right? If I have information, then I have organized way of thinking about things, right? While the opposite of information is entropy, okay? Entropy actually is a term that's used, for example, in physics, in stochastical physics. Physics of liquids and gases, okay? So entropy is the measure of the disarray, so to speak, okay? The higher entropy I have, the more disarray or disorder I have, okay? So here is basically the formula. Again, it's not part of your textbook, so please pay attention, okay? Entropy, let's say I have a bunch of M&Ms, right? Let's use the M&Ms example. When you open up a bag of M&Ms, you see different colors, right? There is a mixture of green M&Ms and brown, and there are yellow and red M&Ms and blue, right? So it's kind of random mixture, right? Well, there are certain percentages, I'm sure, that they maintain, right? But if I have all M&Ms of the same color, say, let's say I'm opening the bag and they're all blue, okay? That's an organized set. They all have the same property. The color is the same, right? But if my mixture is proportionally the same, 20% red, 20% yellow, 20% blue, 20 brown, and 20 whatever green, right? The rest of them. Okay, that means that I have a complete disarray, right? Everything is equally represented. Okay, so this is the highest amount of entropy that I have. Entropy as the measure of the disarray. So in this case, what I can do here is the way to compute the entropy formula. Minus sum. I have to take the proportion of certain item multiplied by the log base 2 of that proportion and add them all together, okay? So let me go ahead and illustrate just for our example, okay? Let's say, hypothetically speaking, that in my set, okay, these 12 people right there, magically, somehow, all of them have the proportion, all of them are yeses. So everybody defaulted, right? That is a uniform group, right? Every single of my customers defaulted. There was not a single occasion when customers did not default, right? So this is a bad situation for me as a bank, but that situation should have minimal entropy, right? Because I don't have a mixture of different states. Everything is one single state. No or yes, right? Yes, everybody defaulted, okay? So let me go back. So let's say that I'm right here. So horizontally, I have proportion of people who said, not said, but who defaulted. Proportion of all people in my set that defaulted, right? So let's calculate the entropy that corresponds. Today I forgot my magical pen that I can use to write things. So I have to type a little bit, right? Okay. So entropy, according to my formula, right? Hold on, I'm going to erase that. Okay. According to my formula, I have to say minus, right? Sum proportion times the log proportion, okay? So proportion of people who said yes, who defaulted on the loan is 1, right? It's 100%. So 1 times log base 2 of 1, okay? And I have to add another proportion. Proportion of people who did not default on the loan. What is that? 0, right? 100% defaulted, nobody not defaulted on the loan. So proportion is 0. I have to multiply it by log base 2 of 0. Okay? So let's see what happens, right? You know what log, right, is? Log is to what power do you have to raise the number 2 to get that? Okay? So the base is 2. I have to raise 2 to what power to get a 1? 2 to the power of 0 equals to 1, right? Any number to the power of 0 equals to 1, right? So therefore, log of 1 base 2 is 0. 0 times 1 is 0. Here, that one, log base 2 of 0 is minus infinity, actually, but I'm multiplying it by 0, so therefore it's 0. Okay, so therefore, that entropy is equal to 0. Remember, we discussed that. The entropy is the measure of disarray. So 0 entropy means that it's a completely organized, ordered set, right? It contains perfect information, right? This set, with no doubt, tells me that every single customer that will come in through the door will default on the loan, okay? It's bad from the banking standpoint, but it's good from information standpoint. Good to know. All of my customers will default, right? I should stop getting the loans out, right? So it's a 0 entropy, complete perfect information. Well, let's go to the other extreme right here, okay? And I have it actually worked out already, so let me erase that. Pretend it's not there. Okay, so I'm going to use the same formula. Now my proportion of people who defaulted is 0, right? So every single customer did not default, right? Perfect scenario for the bank. Bank is happy. Okay, let's compute the entropy. So proportion of yeses is 0, right? Proportion of defaults. Okay, I multiply it by log base 2 of this proportion, which is 0. Okay, and I add to that proportion of no's is 1, right? Yeses are 0%, so ones are 100%, right? Proportion of not defaults is 1 times, again, log base 2 over 1, right? And what do I have? Same situation pretty much. Log of 0 is minus infinity, but I'm multiplying it by 0, so it's 0. And log base 2 of 1 is 0. I have to raise 2 to the power of 0 to get 1. Multiplied by 1 is 0, so 0. Again, I have perfect entropy, right? No uncertainty. Every single customer who comes through the door, regardless of their body shape, head shape, body color, they're all good customers. There are no defaults. I'm a great bank, okay? I have perfect knowledge about my population, right? Now let's take a look at what happens in between. Let's say that percentage of people who defaulted is 50, and percentage of people who did not default is also 50. That sucks, right? Because it's a coin toss, right? Really, at that point. So somebody comes in through the gate, that's my customer, they apply for the loan, and there is a 50-50 chance that he will default or not default. So that kind of sucks, right? I don't know. That's the least amount of information that I have. The highest disarray, right? Okay, so let's compute the entropy. So I'm going to scroll it down a little bit. Okay, so entropy, let me copy paste. Copy and paste. Entropy. So let's start with percentage of people who did default. So yes, that's right. What's the proportion? 0.5. Half of them defaulted, right? Multiplied by log base 2, right, of 0.5. Okay. Plus, now let's take a look at people who did not default. What's the proportion? Also 0.5. Half and half, right? 0.5 times log base 2 of 0.5. Okay. Now so similar things, right? Right here. So how much is log base 2 of 0.5? To what power do you have to raise number 2 to get 1/2? To what power do you have to raise number 2 to get 1/2? -1, right? 2 to the power -1 is 1/2, right? 0.5. So therefore, this log is -1, right? So what I have really is minus -0.5, right? -0.5. Oops, 0.5. And another one just like that, right? Because I have log 2 of 0.5, which is -1, right? Times 0.5. That gives me another -0.5, right? 0.5. So therefore, it's equal to 1, right? Entropy is 1, the highest the entropy can be. If I have a 50-50 mixture, my entropy is the highest. I really have no idea how to separate yeses from the no's. It's half and half, right? So therefore, if I make a chart, let me see if I can insert the line here. Oh God. No. Do you see how can I insert the symbol? I know how it can be done in Word. Oh God. Here, right here. Yeah. Oh, thank God, I found it. Okay, so my entropy starts at 0. It peaks right here at 1, right? And then it goes here to 0. So that's how my entropy looks like. Okay. So the idea basically is that if you're starting with a set that has high entropy, I'm going to split that in 2 subsets, okay? And every subset hopefully will be more organized. It will have not 50-50 mixture, but something like 0.7 versus 0.3, or ideally 0 versus 1, right? And therefore, it's going to have lower entropy, right? And so what I'm going to do is take a look at how I can split the set. I can split the set according to the body shape, to the body color, or to the head shape, okay? So the lower the entropy of my set, the better the information, right? The more informative is the split. So therefore, let's do that. Let's go ahead and compute the entropies of the original set, okay? and also what happens with entropy after I do the split. Okay? And then after that we have to pick the split that has the lowest entropy, right? After that. Make sense? So entropy as the measure of the disarray, disorganization, is what I'm going to do. So let's go ahead and compute the entropy for the first one, right? Of the original set, which is not split. Well, it's not quite 1, right? Because if that would be 50-50, just like in our example before, right? The entropy would be 1.0, right? But it's not a 50-50 split, right? Because I have 1, 2, 3, 4, 5, 6, no, hold on, 1, 2, 3, 4, 5 no's, and 7 yeses, right? So it's not quite 50-50. It's going to be a little bit less than 1, right? But let me go ahead and do the formula right here. So I'm going to say equals to, what do I have to do? Minus, right? And inside the brackets, I'm going to type, what's the proportion of yes, of no's? It's 5 out of 12, right? So therefore, 5 out of 12 multiplied by log of 5 out of 12 base 2, right? So that's my first proportion times the log of proportion, okay? And then plus, so that's no's, right? Yeses are 7 out of 12, agree? The other part of my set, 7 out of 12, right? That's proportion of yeses. Multiply that by log of 7 out of 12 base 2, okay? Kaboom. Here is my entropy. Remember our previous chart? The entropy, the highest that the disorganization can be is 1, right? Entropy is 1, is the highest amount of disorganization, disorder in the set, right? I'm pretty close, right? It's not 50-50, it's more like, yeah, I don't know, 55 versus 45 kind of deal. So therefore entropy is not quite 1, but it's pretty close, right? So that's pretty bad what I had to start with. Okay, so let's split on the head shape, okay? What do I have? Not rectangles, but really squares, right? Square versus circles. So I'm going to separate squares into their own, right? So square, you know what, easier probably is to move circles, right? Now I'm looking at it. So circle, this is circle 1, it goes into its own set, this is circle 2, and that guy is circle number 3, right? So let's take a look at squares first, right? How many squares do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 squares, right? And circles, I have 3, right? Okay. So let's calculate the set, the entropy of the squares by themselves. Okay? I'm going to use the same formula. I'm going to say equals minus sign log. Minus sign. In the square heads, let's start with nodes. How many nodes do I have? 1, 2, 3, 4. 4 nodes, right? Out of how many? 9, right? In the group, right? So therefore, I have 4 out of 9 that are no default. Multiply that by log of 4 out of 9 base 2, right? So that's my no part of my set. Plus, how many yeses do I have? Well, 4 no's, therefore 5 yeses, right? So 5 out of 9 are yeses. Multiply that by log 5 out of 9 base 2, okay? Oopsie. What does it say? Yeah, correction. Okay, so this set has 0.99 entropy. Actually, it's even higher than I had before, right? For some weird reason. Did I do it right? 5.9 and 4.9. Yep, looks like I did it right. Okay, cool. So that's a high entropy set, right? Because the split is almost half and half, right? Completely disorganized. Okay, so circles now. Circles have to be better, right? Because, look at that. Out of 3 people, right? There is only 1 no, and there are 2 yeses. So it's a better split in a sense, right? Okay, so let's calculate the entropy. I'm going to do the same thing. Minus. Here, let's start with no's, right? 1/3, right? 1 case out of 3 cases said no. Times log of 1/3 base 2. And plus, yeses are 2 out of 3, right? 2 out of 3 times log 2 out of 3 base 2. Okay? Kaboom. Yep, it's a better entropy. Look at that. my set is getting a little bit more organization, right? 33% versus 66%, not quite as 50-50, so therefore the entropy goes down. So how do I combine? Now I have to compute the total entropy, right? How about I weight the entropy by the proportion, right? So for example, this set has high entropy, right? So 0.99, but that represents only 9 out of 12 cases, right? So I'm going to weight. The heavier the set, the more it influences the entropy, right? So times 9 out of 12 plus the other set has lower entropy, but it's only 3 cases out of 12, right? So the entropy of that split, is it substantially lower than my initial entropy? No, it's pretty much the same, right? My initial was, when I had almost 50-50, it was close to 1.97, and when I separated based on the head shape split, right? 0.972. Almost nothing happened, right? So is it a good split? Do I gain a lot of information? No. It's pretty much the same thing, right? My entropy didn't change. What I'm looking for is the reduction of entropy, right? Substantial reduction. That's not a substantial reduction, right? So that's probably not a good candidate. Well, let me now explore the body shape split, okay? So I'm going to put these poor people back to their bodies, right? Okay, and let's explore the body shape. Body shape, I have ovals versus rectangles, right? So what's easier for me to move, ovals or rectangles? Doesn't matter because it's 6 versus 6, right? Okay, well, let's move ovals down here. And that one as well, and that one as well, and that one. Oopsie. Okay, and that one as well. All right. So ovals are 6, and the rectangles are 6, right? Well, let's deal with ovals first. Again, same thing, right? I'm going to compute the entropy of the set. All right, so I'm going to say minus. What's the proportion of no's? 4 out of 6, right? So no's are 4 out of 6, and I multiply it by log 4 out of 6 base 2. Cool. Plus, and the yeses are 2 out of 6, right? 2 out of 6 multiplied by log 2 out of 6 base 2. 0.91. Yeah, there is a reduction, right? Compared to 0.97 that I had originally. But is that a huge drop? No, not really. Okay, let's deal with rectangles now, okay? So entropy equals minus sign. So rectangles are up here, right? What are the yeses? 5 out of 6. That's actually much better deal, right? Because 5 out of 6 is almost pure set. If that only guy who is not a default was a default, I would have a perfect situation, right? Unfortunately, not quite like that. So, but it's still very good, okay? So, no's, again, let's start with no's, right? It's 1 out of 6 multiplied by log of 1 out of 6 base 2. And then add yeses. And yeses are 5 out of 6, right? Times log 5 out of 6 base 2. Kaboom. Look at that. There is a substantial reduction, right? From 0.97 I went to 0.65. That's a much more organized set. So now let me compute the weighted entropy of both sets together, right? And they're 50-50, right? 6 out of 12 and 6 out of 12, right? So I'm going to take the first entropy, and that's 6 cases out of 12. Add the second one, and that is also 6 cases out of 12. Kaboom. So between these two subgroups, right, my entropy went down from 0.97 to 0.78. That's a good deal, right? Not perfect, of course, but it's good. So now let's explore the last one, right? So I'm going to put Humpty Dumpty back together again. They do look like Humpty Dumpty, some of them, right? Yeah, poor guys, taking the loan, defaulting on the loan. Okay, so let's separate now by body color, and that's as easy, right? So my grays go here, and my whites stay up there. Okay, so my whites, the split is very uneven, right? The whites are 10 cases, and the grays are 2 cases, right? Okay, let's again compute the entropy of the white set, right? So minus. All right, let's start with no's. In the white set, how many no's do I have? 4? 1, 2, 3, 4. Yep. 4 out of 10 are the no's, right? Let's show. Times log of 4 out of 10 base 2 plus, now yeses, right? So yeses are 6, right? 6 out of 10 are yeses times log 6 out of 10 base 2. So what do you think? Is it going to be a good entropy or bad entropy? Low or high?
High.
Kind of high probably, right? Because the split is close to 50-50, right? It's 40-60, close to 50-50. Yep, and indeed 0.97, high entropy. So it is a disorganized set, right? Doesn't carry a lot of certainty, a lot of information. Well, let's take a look at the gray set, right? And here is perfect 50-50, right? So entropy is going to be what? 1, exactly 1, right? Because it's a pure mixture, right? 50-50 mixture, as disorganized as it can get, right? So the entropy is going to be 1. Just for the heck of it, let's compute it. So minus 1/2 times log of 1/2 base 2 plus another 1/2 times log of 1/2 base 2. Kaboom, here's your 1. And now I mix them together, right, to calculate the weighted entropy of the split, right? So what do? I take the entropy of the large set, this one, and that's 10 cases out of 12, right? Plus the entropy of the smaller set, just perfect 1, times it's 2 cases out of 12. 0.975, okay? So that's basically what Christmas is all about, ladies and gentlemen, okay? So if imagine me, I'm a computer program, okay? This is the way for me to calculate the best split, okay? So my algorithm is like that. You find 3 variables how you can split the set. You can split based on head shape, or you can split based on body shape, or you can split based on body color. Every time when I split, I have 2 subsets. For each subset, I compute the entropy, right? And then I add 2 entropies together, weighted by their coefficients, right? How heavy is the subset. And that's my total, right there, okay? That's variable number 1, head shape. Variable number 2, do the same program, put the set together, okay? Separate ovals versus rectangles, calculate entropies of both sets, mix them together, get the total. That one right here, okay? And then put the set together again, separate based on the body color, and do the same program, compute the entropy. And go with the one that gives you the lowest entropy. In other words, that carries the highest amount of information, right? And that would be your best split. That's essentially how the program does that, okay? So there is no big mystery. The program literally goes through every possible split, and it says, yep, on every step, let's compute what would be the best candidate, okay? So we have about 7 minutes remaining. Let's see how JUMP does that, okay? I understand this stuff is boring. Formulas that you didn't see before, right? Entropy. How many of you heard the term entropy before today? Heard it before. Okay, good. But most people aren't familiar with that, okay? So let's see how JUMP does that, okay? So for that matter, let's go ahead and go to Scholar. Okay? Go to Scholar. And right here is the folder that has JUMP files. Okay? So go to JUMP files. Do you see the file recursive partitioning? Yeah, download that file. It actually contains exactly same stuff as we just did, okay? So what I wanted to show you is, first we did it manually in class, right? I gave you the pieces of paper, you started to shuffle them and said, yeah, looks like, based on the body shape is the best split, right? And then what happens next, right? How do you split the resulting groups further and further, okay? But, of course, nobody does it manual, right? So what we did in class doing this manual exercise and what we did today, calculating the entropy, I just wanted to show you kind of nuts and bolts, the principle, okay, that the software is using in order to calculate the best way to split the sets, okay? But let's see the software in action. So go ahead and double-click the file, and it will open up just like that. So what we see here is exactly what we did just now, right? There are 12 customers. Look at that. Some of them are no, they didn't default on the loan, and some of them are yes, they did default on the loan. So this is my target, right? Loan default, the variable loan default. That's what I want to predict. That's my target variable, right? Yes, no, two possible values. Then customers have head shape, square versus round. They have body shape, oval versus rectangle, and they have body color, white versus gray. So that's exactly the same set as we had before as the stick figures, right? Okay, so let's see how the software does the split. Okay, so what I'm going to do is, let's see, go to the menu Analyze, okay, and in the menu Analyze, go to the Predictive Modeling, because the majority of the models that we're going to do in this class are predictive modeling. Okay, I'm trying to predict the value of my target variable, whether it's continuous or whether it's categorical. Oh, by the way, before we go there, look at that. What are the types of my variables? Nominal, right? All of them are categorical nominal variables, right? My target is nominal, which is loan, default versus yes or no, right? And my head shape, body color, they're nominal, right? There is no ordering and they're categories, okay? So target and the predictors, they're all nominal. Okay, good. So now let's go to Analyze, Predictive Modeling. Do you see partition?
Yeah.
Yep, go ahead and do the partition, okay? And it's very easy to set up, okay? First of all, what's my response? Response is the same thing, response variable or target variable or dependent variable. They're just different names for the same thing. Okay, so what's my response that I'm trying to predict?
Loan default.
Loan default. So I'm going to say, yep, place loan default in there. And X factors are predictors, what I'm using as independent variables that will tell me whether or not customer is default. Okay, so I'm going to select all three of them, just like that. Put that into the predictors, and that's it. I'm ready to cook. Click the OK button, all right, and it tells you, yay, look at that. Now, what I want to do probably is to go to the red triangle. Remember that a lot of options that we may want to display or use in JUMP, they're hidden under the red triangle menu, right? So go to the red triangle and say Display Options. There are two things that are not showing. Probabilities, split probability and split count. If you pick split count, it will show both of them, I believe. Yeah, split probabilities and the split count. Okay, so that's my initial window, right? Okay, so go to the, you can probably see the candidates, right? This is my original node, by the way. Okay, that's my everything, the whole set. All right, it says the count is 12, all right? Out of these 12, there are 5 people who said no, who did not default on the loan, and there are 7 people who did default on the loan. That's my starting point, unsplit set, okay? And if you click candidate, it expands, right? So it says that right now, I can split on 3 different things. I can split the set based on the variable head shape, or body color. And what it does basically is it computes for each split, it computes a measure called log worth. I'm not going to go into the details because it's even more boring than what I just showed you, okay, with entropy. But it's trying to find the highest measure, which is log worth, okay? The higher, the better. So therefore, out of 3 candidates, it's going to pick which one? Body shape, right? And you can see that it says, this is my split cut point, right? And it puts the star against that. It says, that's my best split, okay? So now what I can do is, and by the way, this one, it basically shows you the breakdown. The yes between yeses and no's, right? Because here I can see that the split really is 41%, 41.6% of no's. That's my bottom half, right? So this horizontal line shows you the split basically, right? The proportions, okay? And 58.3% right here are no's, okay? So when I click the button split, guess what it does? It says, yep, that's how I'm going to split my set. That's the best thing to do, right? So right now I have body shapes, 6 versus 6, right? Rectangles versus ovals. And it can split even further, right? Right now it's not showing anything for a reason that I will explain to you in the next class because I ran out of time. Okay? So we're going to pick up right here next class, and I will show you more examples. Okay? So we'll start learning how the classification tree works.